Alright, so we're going to get this started. Today Goran's going to talk about distributed computing with shortcuts.
Thank you, Nama. Okay, so the topic today is how to construct simple and fast protocols that you can use in the field of distributed computing. So in particular, the main topic of today will be concerned with minimum spanning trees, or MSTs. So just as a quick reminder, what is a minimum spanning tree? Well, you're given a weighted graph, and from all the huge number of trees, pick the one that has minimum sum of weights. So that's it. And the main problem we're dealing today is find the minimum spanning tree of the internet. That's the easiest way to put it. So you have like a huge number of computers on the internet. All of them can compute something. The diameter of the internet is like fairly small. It has like a tree logarithmic tree structure, so the diameter is kind of logarithmic. And we're in the business of designing protocols. So these are like computers. Nobody knows the entire topology, and you want to make them communicate efficiently in a small number of time to compute something. Okay, so let's define the model we are working in a little bit more formally. The model is called the Congest Model, very popular in the field. And basically what it says is that the internet, the graph, is communicating in synchronous rounds. On each round, each node sends log n bits to each of its neighbors. N is the number of computers in the internet, so log n, you can send a couple of identifiers of computers. That's basically what you can send in a round. The rounds are completely synchronous, no failures, and you want to design a protocol that will compute the MST in the minimum amount of rounds. So initially, the nodes are very stupid. They only know their immediate neighborhood, nothing else. You want to minimize the number of these synchronous rounds to solve a problem. And as you can see, this is more of a problem of information complexity, communication complexity. Because the main deal here is how to actually communicate such a strong and complicated problem in this logarithmic number of bits per round. Okay, so let's build some intuition.
So it's log n bits per channel or per?
So each node on each round sends log n bits to each of his neighbors.
Right, only.
Yeah, only. And he can even send different things to different neighbors. So think about it that the bottleneck is on the time it takes the information to travel from one node to the other. Okay?
But they're not bandwidth limited.
No, it's not like you have some wait time and then you have large bandwidth. No, you're just saying this is a simplified model. It says log n bits takes 1 round, 10 log n bits takes 10 rounds.
On the complete graph?
Between two neighbors. So some nodes that are far apart have to take a long number of times before they can actually hear from each other. Okay, so how to actually do the leader election in this model? Let's build a intuition. Well, normally in like centralized computing.
But edge weights, I mean, they are what? Real numbers? Because you need some kind of assumption on how to decode them.
Okay, so edge weights are only an artifact of computing the minimum spanning tree. So an edge takes 1 round to communicate with each other. The weight is something completely unrelated. It's a number that's, let's say, how much do you need to pay to buy that cable? So think about communication time as 1 round between two neighbors, and the weight is some other number that is associated with the edge. It has nothing to do with the time of travel.
Right, but if I want to communicate the weight on that edge,
okay,
somebody else, how many bits do I need to present that?
Log n. That's.
So it fits in log n.
Yes, it does. I should have said that. Yes, definitely. Okay. So how to do leader election? Leader election means you have the entire big graph and you want to pick one node as the leader. Everybody must agree on this. It's a non-failure model, shouldn't be too hard. So what can we do? Every node picks a unique random ID. you pick 10 log n bits, and with high probability, everybody will have a unique random ID. And then you just need to pick the minimum one. So each node communicates for diameter number of rounds. And so each node communicates the minimum ID it ever saw for a diameter number of rounds. And then you can imagine the minimum ID in the target graph was spread to all the else. And after diameter number of rounds, everyone will know this. So that should be clear. And that's exactly what you can do. So note here that in normal, like algorithmic complexity, you usually describe like time or complexity with n being the number of whatever elements you're given. Here we are actually doing it in the way of diameter. That is like a more fine-grained measure. Sure, d is up to n, that's clear. But usually, such like in this internet like graphs, you can see the n is huge, but the diameter is much smaller, so it's much better to have something on the order of d.
So the diameter needs to be known?
Not really. I mean, sure, in this case, well, yeah, in this case, we assume that we do know the diameter. There are ways to go around it, but to keep it simple, let's assume that we do know the diameter. Cool. You don't really need to know them. You can guess it exponentially, and then you can check, and it works. Okay. So similarly, you can construct a BFS tree in diameter rounds. So like every node will know which one of his incident edges are part of the tree, or you can compute the number of nodes in D rounds, the exact number of nodes. But the question is, can you do the same thing for the minimum spanning tree? And the answer is surprisingly no, you cannot. It's much more difficult. Surprisingly, there is a lower bound for the minimum spanning tree problem. And it says you have to take diameter plus square root n number of rounds. And it also holds for a bunch of other problems, like the min cut, or the shortest path, and so on. And we don't really like the square root of n because it's huge. So in the internet, well, n is 1 billion, square root n is 30,000. We don't want to take 30,000 rounds, we want to take 100 rounds. That would be the diameter. So just in this lower bound, it's kind of clear where does the d come from. Because if you have two nodes that are very far apart, d apart, you cannot really check. It has to take at least d round. You have to have at least d rounds until one node hears from the other. And without that, you cannot even check, is it a normal spanning tree? Is the spanning tree connected or not? So, yeah, the d is clear, but the square root n one is not really clear. And I'll try to give you intuition why does the square root n come from by giving you the exact lower bound example, the lower bound example graph.
Okay. So it's square root not for every graph. It's just for there is a graph for which
yes. Exactly. So it's existential. I mean, there exists a graph for which you cannot do better. So it also means there exists no algorithm that works better than this time. Yeah. So I just get some intuition. Why does this graph not work? So how is it constructed? You have square root of n paths of length square root of n. You have a binary tree on top of it. And everybody on this level is connected to the leaf of the binary tree. Everybody on this level is connected to this leaf of the binary tree. This is the lower bound graph. The number of nodes in it is about n. So n. The diameter of the tree is log n, so very small. Like you can go from any node to any other node by going up to the leaf, then going up to the tree, then going down to the leaf, and down to the other node. So the diameter is log n.
And there are horizontal edges?
Which one?
Or the black one? The black one is an edge?
Yeah, this is an edge, and this is an edge.
That's not a complete graph on that level. It's just a path. Horizontal, it's a path.
Oh, horizontally, exactly, it is a path. These two are not connected.
Okay.
And the entire gist is that these two nodes cannot really communicate in a fast way without going through the tree. And when you compute the MST, you actually want to all these pairs together want to communicate with each other. Like this one to this one, this one to this one, this one to this one. So square root of n pairs of them.
What is the tree? The minimum span?
Yeah, what are the weights there?
Depends on what you set the weights. But I'm saying I can set the weights in such a way such that this reduces to some set disjointness problem. And basically, in an intuition, like on a level of intuition, you have to communicate between these square root n pairs of nodes. And if they want to communicate faster than the length of this path, they all have to go through the tree. But you do not have enough bandwidth in the tree. The congestion will be too large, and you cannot do that. So yeah, this is the example why you cannot do it faster than square root n, and that's about it. So it also was known for a long while that there are matching upper bounds or algorithms that actually work in about the same time as the lower bound. So throughout the lecture, I'll usually ignore polymorph factors to make things simple.
About that square root of n though?
Yeah, please.
Why is it square root of n? What if you made the diagram? It's not a symmetrical diagram. Well, if you made it wider, but end of the 2/3 by end of the 1/3, why wouldn't it be end of the 2/3 down lower bound?
Oh, because then they can go through the tree. So the tree actually supports square root of n pairs, a little bit less, and you can go like this length, square root of n. So basically, if the path is wider, the tree has more bandwidth, and everything could go through the tree.
Oh,
So
people end up with more bandwidth that way.
yes, because if it's wider, the tree is bigger, and it has more bandwidth. Does it make sense?
Not really, because the root of the tree is, everything still has to go, I mean, a lot of stuff still has to go through the root of the tree.
Well, not really through the root.
Yeah, I guess.
I mean, you can, so basically you can prove like a fourth root of n by just keeping one node here and connecting it to everything. And you can prove like root n, so it's not that problematic. You don't really need to go through entire sum. I mean, you don't need to go from one end to the other. You can bypass it. You can go from like middle to the end. So the math works out, and actually the wider the graph is, the tree has more capacity. They do not really have to go through the root. They can bypass it lower, and then they can bypass it lower again. Going through the root is like...
Are we assuming
for a couple.
randomized?
Yes. So the reduction is to set the disjointness problem, which has a randomized lower bound. This is within randomized. You cannot do anything better. Yes. Okay. So there is also a matching upper bound. Like all of these algorithms have a matching upper bounds, and it appears that the issue is closed. Like you have a lower bound, you have a matching upper bound. What more is there to do? But the problem lies here. Like, let's say you actually want to solve the MST for the internet graph. Sure, there is a lower bound, so what are you going to do? Are you going to raise your hands up in the air and say we cannot do anything? Or the other way is to actually see that the internet has like a lot more structure than some other graphs, general graphs, or in particular the lower bound graph. Like, is the internet exactly the lower bound graph? Probably not. So there is a chance that we can do something better. And people actually care. Like, there exists an implementation of the spanning tree protocol that basically computes some kind of a spanning tree, not in square root n time, but it is out there. People do care about these kinds of problems. So, can we do something better than what would the lower bound tell us? Yes, for certain kinds of graphs. And the way how we do it is by using a framework called shortcuts, which I'll introduce throughout the lecture. So basically, it's a framework that will allow you to make like simple and efficient protocols to solve problems such as the minimum spanning tree. And to give like a little brief history of how did the shortcuts come to be, they first appeared in 2016 in Soda, and it was the first paper who ever went below the square root n lower bound for any problem. And it proved that you can solve the MST on planar graphs in order d rounds, which is perfect. This is basically exactly what we need. We want to solve it in d rounds. So the only problem there is that the construction of these shortcuts was very complicated. You basically needed to find a planar embedding. And that's not an easy way, that's not an easy thing to find in a distributed manner. You have the same bandwidth issues and all that thing. So this was by Mox and Ghaffari and Bernard. Then a paper by Bernard, a collaborator from Japan, Taisuke Izumi, and me. In Pozzi, we simplified. The paper simplifies the framework. And most importantly, gives efficient construction. So basically, it simplifies the construction of the shortcuts. If you make the definition a little bit stronger, you can make the construction much simpler. And now you can actually do the same thing for genus-bounded graphs. And in a subsequent paper with the same authors, we found that you can do the same thing for treewidth-bounded graphs and a little bit better constant for genus-bounded.
Just to make sure I understood, like the graph is planar, but the nodes know nothing about like the planar embedding.
Yes, exactly.
Okay.
Well, yeah, if the nodes knew about the planar embedding, in particular if they knew about the one ordering of the edges that is consistent, you could do this in a much simpler way.
They have the embedding.
Yeah, what's up?
What's the genus that we have?
Oh, sorry,
What's the genus?
a genus. Oh, well, when you have a planar graph, they're genus 0. Then if you have like a donut graph, you have genus, let's say, 2. Well, it's basically, it's a manifold thing. It counts the number of handles you have on your manifold. But it doesn't really matter. You don't need to know neither the treewidth or the genus boundedness. What is a genus nor a treewidth on in any graph. I will not deal with that here. Okay. So what are we going to do now? I'm going to motivate the shortcuts and their definition by representing the classical MST algorithm of Boruvka. We're going to define them. We're going to say why they're useful. We're going to once over go through the graphs that have good shortcuts. And then I'm going to talk very briefly about how to construct the universally nearly optimal shortcuts. Okay, so the classical algorithm of Boruvka for computing the MST goes like this. You have a graph. In the beginning, you have a graph and you maintain a vertex partition. You maintain a bunch of clusters. In the beginning, each node is a singleton cluster, and then they merge together. And each cluster maintains a minimum spanning tree within itself. And the algorithm says basically one thing, very, very simple. Each cluster picks the minimum outgoing edge from itself, and that merges with the cluster on the other side of that edge. Edges that edge to the MST, and then merges to the one on the other side of this edge. So I just wrote it out, and the picture is the one you have to worry about. You pick the minimum weighted outgoing edge, and then you merge with the cluster, and now in the next one, this becomes a new cluster. And that's it. This is the old algorithm of Boruvka. So it takes actually only a logarithmic number of rounds, but like the number of times you have to merge everything together. But the main sub-problem in this looked like this. The main sub-problem you had to solve when you were actually doing the algorithm of Boruvka. You had a vertex partition, and you want to pick the minimum outgoing edge out of each cluster or part. I'm actually going to call the clusters parts for now. Parts now because it's consistent with the literature. So you have a partition into these parts, and you want to pick the minimum outgoing edge for each part. That's the main sub-problem you have to solve. Or more generally, you have a connected, like you have a vertex partition such that each part is connected, and you want to compute some simple function of its vertices, like computing the min in this case. Computing the min for every part in parallel. So this is like how it looks like. You have like a graph, but then you have a vertex partition. It can be strangely shaped. You cannot really control how the parts look like. And you want to compute the minimum within each part. And it actually, if you can solve this subproblem efficiently for an adversarial partition, because you cannot control it in a fast manner, you can solve the MST in a fast manner. Like if you need f of the rounds to solve one of these partitions, compute the partwise minimum, then you need a couple of log factors more to solve the entire MST problem. So this is the main issue we are dealing with. And the shortcuts are a way how to solve this problem.
So I missed something. You just mean compute the partwise minimum spanning tree?
No, just the partwise minimum value. So every guy has a scalar, a value. Every node in a part has a scalar. For instance, and you want to compute the minimum out of all the scalars within your part. And you want to broadcast this to everybody in your part so that they know. That's everything you need to know.
And each vertex knows that it's part, like these guys know I'm in part 4.
Well, yeah, they know the idea of the part. They do not know how many of others are in the same part. They do not know things like that. They just know their idea, the idea of the part. Okay, so what is the naive solution? Well, naive solution, just say, well, you want to solve something within a part, communicate within a part. What's the big deal? But the problem there is that the diameter of a part can be much bigger. Like as we saw here, maybe there is like a nice spanning tree, BFS tree that is very shallow, so the diameter is small, but the part can go like a snake. It can have a huge diameter. Like in the lower bound graph, the diameters will go again, but each path in isolation had a square root 10 diameter. So we cannot really do communication only within a part. So what's the next most natural thing? So this is just an illustration. This is like some BFS tree for reference, and then we have a bunch of parts, like bool part contains all the nodes that like fit within this thing, and they want to communicate with each other. So this is like a diagram, and they're somehow connected on non-tree edges, possibly. So they can be like very wide, even though the tree is shallow. So okay, we cannot do communication within a part. So what's the next thing we can do? We can add things to a part. Like we add other edges, for instance, of this tree to a part, and lower its diameter. So for instance, like these two nodes can communicate very efficiently if you were add everything like from this end up to that end inside. If you were add this shortcut to the bool part, then this part could communicate efficiently. Like for instance, these two nodes in the end could communicate in diameter time because the tree has depth diameter. It's a BFS tree. If you were to give it all the edges like up above the part itself. And that's exactly what we're going to do. So these are shortcuts. You are given an adversary fixes a connected vertex partition, so the parts, and he also fixes a spanning BFS tree. And we want to add edges to the parts as to make the diameters of the parts very small. And not only that, we're actually going to restrict ourselves to adding only the edges of the tree. It's not really clear why it's sufficient, but it basically works. We don't know any reason, any way why it's not good to add that. Why, does it ever make sense not to add edges of a tree and add something more? We actually do not know.
But I thought you were worried about congestion. You're not worried about congestion.
I am. I didn't say that, but I'll just go over that in a minute. Sorry. Yeah.
Is each edge added to a single part or multiple parts?
Yeah, that's the question. So actually, each edge can be added to multiple parts, but you have to be careful. So you want to add, so for each part you want to add a bunch of edges to it because it will lower the diameter. But if you add every edge to every part, it will kill the congestion. It will raise another issue on the other end. So we actually have to balance this in some sort of way. So, and that's exactly how are we gonna estimate the quality of a shortcut. Okay, so let's go one by one. So a shortcut is basically you have parts and you add edges of the tree to that part. Like the blue part, you add blue edges to it, to the green part you add like green shortcut edges to it, to the red part you add this. Great. That is a shortcut. That's the entire that's the framework that the lecture is about. So as we said, we have a couple of quality parameters. One of them is called congestion. And it says that no edge is added to more than C parts. Then we say that the congestion is C.
That diagram is a little bit confusing because you used the red color, for example, to apparently isolate a set of vertices, but also to show edges in the graph. Am I misunderstanding?
So this is like, you can imagine that all the vertices in here are within a part. And this is my shortcut edges that I add to this part to make the diameter smaller. And you can have like multiple edges, you can give this edge to multiple parts, like the red part and the green part. It will have congestion 2 on this edge. Does this answer the question?
Yeah, I guess.
Okay, so yeah, basically everything, the red edges I add to the red part. Okay, so that was congestion, one quality parameter. The other quality parameter is called the block number. And this is what it basically says. So look at everything that is given to the red part and only focus on the tree. So there are a bunch of non-tree edges that we are ignoring, but let's delete them out. Then the red part decomposes in a couple of components, in a couple of subtrees. We call each of those subtrees a block. And the maximum number of blocks in any part is called the block number. So for instance, if no part will contain more than 5 these subtrees in isolation, then the block number is 5. And that's about it. This is one slide you might want to remember, kind of. But yeah, so we are given a partition, we are given a spanning tree, BFS spanning tree. You want to find such a shortcut to those parts as to have a low congestion and a low block number. The lower you can get, the better. There is a trade-off, which I'm going to discuss now. So, let's say that you did that. Yeah, please.
Sorry, what is helpful about having a low block number?
Oh, because if you have a huge block number, then it's not really clear how to efficiently communicate between them. So you can imagine you have like, whatever, n of the blocks one by one. You cannot really efficiently communicate because in a block, block has an efficient way of communication, as I'll say it soon. But between blocks, you have to go edge at a time. So, exactly as Alice asked, I want to now say, when you actually have a good shortcut, you can spread information in a part very efficiently. And that's exactly how it goes. So if you have a part with like B blocks, you can communicate within a block within D plus D, 2 diameter things. So the tree is, as I said, the tree is a BFS tree, so it is shallow. So the height of the BFS tree is D, the diameter of the original graph. So in each block, you can communicate between in 2D routes. You just go up, broadcast up, converge cast up, broadcast down. That's all that you need to do within a block itself. But the problem is when you have multiple blocks, you have to go like one edge. You basically have to communicate in a block, then go to the other block, then communicate with the block, then go to the other block. That's the worst case that can happen. So, yeah, we'll see later how does it work. But the idea is if we have small block and small congestion, block B and congestion C, we can compute the partwise minimum in B times D plus C number of rounds. Good. So, the thing you need to remember, small block and small congestion, we can compute the minimum and spread it around in this small amount of rounds. And now, more importantly and much more surprisingly, we have the construction lemma, which is the gist of the entire shortcut theme. And this one is very interesting. It says this: if there exists any good quality shortcut on it, we can actually find it. So it doesn't matter what the graph is. If there exists a good quality shortcut, we can find a good quality shortcut with a little bit of worsening in the parameters in a small amount of time. And even better, the algorithm basically does not even depend on what the underlying graph is. It can be planar, it can be genus-bounded, it can be treewidth-bounded. You really do not care. You can find the good shortcuts just by the virtue that they exist. You can find them. So this is what the lemma basically says. If the graph has shortcuts B and congestion C for every spanning tree T, but that's a technical issue, we can construct about BC shortcut, block B congestion C shortcut, in basically the same amount of rounds as you need to spread the information in one part. So that's very interesting, and that will be the gist of the entire thing. So you can find universally optimal shortcuts within a graph. And I even conjectured it can be like, useful in practice. Like you don't need what the graph is. The algorithm is uniform to what the graph is. You just run it. It will find some good shortcuts. And because a real world graph will have good properties, good. We're good. We find the good shortcut that they exist. So, what will be our solving strategy? How are we going to work with this? We're going to take a graph which presumably has a good shortcut. Let's say, maybe we know it's planar, and we did a mathematical non-constructive proof that planar graphs have good shortcuts. Great. That's all we need. Then we can construct them with a uniform algorithm that doesn't really care what the graph is. And then, using the routing lemma, we can use this constructed shortcut to actually spread the information around in an efficient manner and come up with a fast distributed algorithms for that problem on the graph G. Okay, so let me go one more time over the routing. When you actually compute the shortcuts, how do you route in it in a high-level way? So let's visualize a spanning tree in this way. This is a part, and these are the blocks of the spanning tree. So how do you communicate within a block? You can spread information around. You go converge cast up, broadcast down. Everybody can synchronize within a block. And then you basically have you can imagine having a supergraph where each block is a supernode of B nodes. So the diameter of that graph is B. So you can spread information in B rounds within the supernodes, and each supernode synchronizes within D rounds. So it's about B times D. But keep in mind, this is for one part in isolation. You have multiple parts, all spread around the graph. They are not shown here. And you must do this in parallel for all of them. And then you can do the same thing with a little bit of extra rounds. So you just imagine the diameter is enlarged by C, and you can actually spread everything in parallel. And this is where the C comes on. So if you give all the edges to all the parts, B will be 1 always, but C will be huge. It will be n, the number of parts. That can be, billions. It's not really bounded. So yeah, that's the way. I'm not going to go how you actually do it, but it can be done. It's not that hard to see once you know it's true. So yeah, one more time. The graph that have good shortcuts, now expressed as through our quality parameters C and B. When you have planar graphs, you can have order D, order 1 shortcut. So you can make, what did we say? D, we said that the running time is B times D plus C. So the running time of the MST algorithm can basically work in this amount of rounds. Or we can spread information or anything else. So for the genus-bounded graph, you have this, and for the treewidth-bounded graph, you have basically the same thing if you think about the parameters as being a constant, as you typically do.
So earlier you said you could use square G?
Yes.
Is that a different construction then?
Yeah, it kind of is. I just wanted to keep it simple for if you want to do. So there exists in genus-bounded graph, there actually exists like square root of GD, but you need a little bit different algorithms for that. If you multiply it out, this like be a little bit too much. It can be done, but we don't need to go with it. And in a typical case, G is total as a constant, so we don't care. Yeah. So now we went through the routing. So let's talk about how to actually construct them, like the main gist of the paper. Here is the construction theorem in a little bit more detail.
Next question going on. So is there a matching lower bound of some kind? Like if the block parameter is blind and congestion is blind, and also you actually need so many rounds. Like, you know, the generalization of that example you showed in
I see.
number of slides before.
I see. So you're saying, is shortcut the best way to solve a problem? I would say, in general, if you take the most general, the answer is no. Well, you can make a graph where you can do something better than find a shortcut. But they are pathological, and we don't know a big class of graphs. And even better, all the algorithms that I know, at least, like if they can run in a fast way, you can construct a shortcut in a fast way. So if you're looking only, if you want to restrict yourself to some kind of combinatorial nice algorithms, you can claim something like that you cannot do anything better than a shortcut. And then you will have like an universally optimal algorithm in it.
So there is a well-defined class of algorithms for which you can achieve pure lower bound.
Well, we never really formally defined it, but I suspect that's the case. It really seems that way. So I would say probably in some kind of a very formal way. Okay, so the construction theorem in all its glory. If given a spanning tree that there exists a block B congestion G shortcut, we can find some shortcut that has at most 3 times the block and at most log n times the congestion. And we can do it in our usual number of rounds, the same one you need even to compute the parties minimum. So if a graph has good shortcuts, we can find them efficiently. Okay, so I'm going to briefly glance on the algorithm, how does it work, in a very high-level view, just to give you a feeling for it. So the idea is you have a graph and a bunch of parts in the graph, the partition. Well, and the parts are huge and they want to communicate more efficiently, so they want to take as much of the BFS tree as they can. If they take the entire BFS tree, well, then they can completely communicate within D rounds. That you cannot do better than that. So if you can give the entire BFS tree to each part, you're done. You're great. But you cannot do that because the congestion will be too much. So let's try that idea. So we have a part, and it starts taking all the edges above it in the tree. So we have a part, and it starts taking the edges above it. And then, if, let's say, nothing bad happens, it takes everything, and everything is good. But it could happen that an edge is taken too many times by too many parts. So the congestion of an edge is too much. And then what do we do? Then we just delete an edge. Delete this over-congested edge. So it's pretty simple. We have every part, start taking the edges above it one by one as much as it can, and when an edge gets over congested, as in it's taken by too many parts, we delete it out.
It's deleted from every part's shortcut, or like
Yes.
anyway? Okay.
Every part shortcut. Like, it's easier to prove something there. Like, we don't need it anymore. And if that is the case, if you do the algorithm, you can prove that half of the parts will actually have shortcuts within the range that I described in the earlier scribe. Like 3b, constant times b, and constant times c will have that quality parameters. So what do? You just remove the parts that you found good shortcuts for, and you repeat the process log n times until you found the good shortcuts for all the parts. And that's basically it. So each part tries to take the edges above it. Whenever something is over-congested, when an edge is over-congested, we delete it. And in the end, we'll have half of the parts having good shortcuts. So we delete them out, repeat the process again. Great. I mean, it's a very high-level thing. We need a lot more details. So in particular, we'll start taking the edges from like the lowest level, then one level up, then one level up, and so on. So we'll take like the edges on a level per level basis. And that will give you something. And you need to improve the efficiency, and for that you will use some random sampling techniques. It's not that hard, but it's still surprising. With this like simple algorithm, you can actually find optimal up to logarithmic factor shortcuts. But also you can actually see here that we actually have to know C in advance. And B. Actually, we also need to know B to check is a part good. We actually have to know the parameters in advance. But you can go around that by some kind of an exponential search. You would exponentially search the like B, D plus C, and you can get around knowing them beforehand. So, as a final note, that's it. And it's important to know that the framework works for other poles, most notably Mincut, and probably more. It does not work for shortest paths, or at least not in an easy way. Maybe it can be modified. But the hope is that we could get something good, like below square root 10 for the shortest paths with this kind of framework. So yeah, in practice this could be useful because it's a very simple algorithm that's uniform over all graphs. You don't really care what's underlying as long as there is a good shortcuts. For the overbound graph there will be no good shortcuts, so it will find you a square root 10 shortcut. For a graph with a lot of structure, it will find you something good. You don't know in advance, but then you construct it. You cannot do better than that. And like another interesting open question that we are interested in, like, does there exist shortcuts for all minor restricted graphs, or even any? Yeah, let's say for all minor restricted graphs, or for some particular minors that you are interested in. So, if you could only prove this in a non-constructive way using the most heavy-hitting techniques you could, you would actually be able to claim that you have a simple algorithm for them just because of the way the shortcut is constructed, which is, amazing. So that's it. Thanks.
There's another area called oblivious routing that sounds very similar, right? There's Harry Reiki and stuff, right? So the idea there is you have a bunch of routes you want to do in your network, and but you're not allowed to globally look at the network, but you need to figure out how to send packets not knowing the total traffic. In some sense, it seems like very similar to yours, right? And so then you get these log.
I never thought about that.
In the end, aren't you just getting a route for all pairs or something?
Yeah, so that would be the case. Let's say that Oh, I see. So if a part wanted to communicate only with itself, like you
You
wanna,
can't decouple your algorithm and define me a routing scheme and then use it throughout the life of the algorithm? You're saying you have to do something more complicated to get this to work?
In
No, no,
particular, I don't think
no.
you actually get the tree, right?
Yeah. So you don't know the topology.
Yeah.
In WS routing, you know the graph, you just don't know the demand structure.
Oh, I
Yet
see.
you don't know the topology.
So it's both harder and easier, right? In the sense that with oblivious routing, you know the topology, but you don't know the demands. Here you know the demands,
Oh,
but you don't know the
I see.
topology.
I see.
Sounds like a
So
dual.
this doesn't give you an oblivious routing scheme?
Definitely not directly.
No, because it adjusts to what demands. I mean, the algorithm specifically builds shortcuts according to the demands that you have. It's not kind of one set of things which works for all demands. But on the other hand, you don't need to know the topology.
So you mean it's a non-oblivious routing scheme?
It's a non-oblivious routing scheme,
Okay,
but
good.
it doesn't need to know the topology. It's distributed.
But the final answer is like Reiki doesn't. You just have a bunch of low stress spanning trees.
Yeah, wouldn't it be clear about, I mean, how do you, if you don't know the topology, how do you complete
I
the
know,
low
I
stress?
I'm just trying to fit all this together to start
I mean,
doing.
they're very similar problems, but I think they're.
Yeah, I'm not sure actually what's the correct definition, as Bernard pointed
So
out.
if you have to route for hops more than log n long, don't you have to keep know about the names of all the things you're routing through?
No, because the way they're routing, it's more like spread information everywhere you can, and after X rounds, everyone will get it. That's how the subroutines look like. You actually do not care.
Somehow these routes only occur in the analysis, is that right?
Yeah. So I mean, yeah, the algorithm itself is very simple. It's say go up in the tree, go down in the tree wherever you can for this amount of rounds, and then spread information wherever you can. They're very simple.
So in particular, you can't get the actual tree out of this, right? You only get a value.
Oh, I mean,
No, like in this model, you can't really return a tree at all, right?
oh, I mean, who knows the tree? Every node knows a part of the tree, but who knows everything? Nobody.
Right, right.
That's the problem. Like, you don't even have the bandwidth to,
Right, right.
you know, move the tree around. Yeah. Okay. I don't know. Anyone else? Questions? I guess not.
Let's thank the speaker again.
That's it. Thanks.